Welcome and thank you for joining us. My name is Dean Lee and I'm Professor of Physics here at FRIB, or the Facility for Rare Isotope Beams. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, performers from all fields, and strengthen ties between Michigan State University and the community. Today, we have the great pleasure of presenting a public lecture by Professor Manuel Calderón de la Barca Sánchez from the University of California, Davis, entitled Beautiful Melting, the Dissolving of Beauty and Anti-Beauty States in the Quark-Gluon Plasma. Professor Calderón is originally from Mexico City. He joined the relativistic heavy ion group at Yale University, where he completed his PhD in the field of high-energy nuclear physics. His work was done at the relativistic heavy ion collider at Brookhaven National Laboratory, where he was first a postdoc and then a staff scientist. His desire to teach led him to look for university positions, and he was hired as an assistant professor at Indiana University in 2004, then at UC Davis in 2006, where he is now a full professor. He is also the featured scientist and narrator of the IMAX film, Secrets of the Universe. An enthusiastic educator, he was a recipient of the UC Davis Distinguished Teaching Award for undergraduate teaching. He is also a member of the Nuclear Science Advisory Committee and continues to do research at Brookhaven National Laboratory, as well as CERN in the Large Hadron Collider, focusing on B quark-bound states and Z bosons. So today we have an in-person audience, as well as an audience on Zoom. So for those of you on Zoom, if you have questions, please type them into the chat or the question and answer dialog box. If you have questions in person here, just raise your hand. And for those of you in person here, if there is an alarm or some emergency, we will exit the building through the doors that you entered earlier. Now, for those of you also in the audience here, if you have not done so already, please silence your phones. And at this time, it is my great pleasure to introduce Professor Calderón.
Thank you, Dean, for the kind introduction. It's a pleasure to be here. My first time visiting FRIB. I had visited MSU before, but my first time visiting the new facility for rare isotope beams. Just took the tour and it was wonderful. So what I'd like to talk to you today is what I've been working on basically over the last 10, 15 years. And I've been focusing on working with beauty quarks. And so I'd like to tell you the story of why I think they're interesting and why I spend so much time working. Let's see. Do I see the right place? Yes. But starting from kind of like where the big picture of the various studies that we did, not just me, but everybody in my field, since here at FRIB, a lot of the focus of the radioisotope beams, as for example, I was talking with one of the grad students who was working on the R process, for example. And she was saying, well, I don't know that much about the Quark-Gluon Plasma. So I'd like to, kind of talk about like, what is it that we do in those other facilities? So I'll talk about quarks and gluons and the strong force, the strongest force of nature, the color force. And then focus on why heavy ion collisions can tell us something about this funky state called the Quark-Gluon Plasma. And then talk about my particular emphasis, which has been looking at beauty production and beauty quark states, and try to tell you that we can learn something really cool about the Quark-Gluon Plasma by looking at beauty states. Answering questions like how hot does it get, and can we really see the color force acting? And so I'll talk about some of the beauty measurements that I've worked on and emphasize, I think, mainly the ones that I've been doing over the last 10, 15 years in CMS. So since we're talking about fundamental forces, usually one of the things that I like to do is start with something that is familiar, because we're going to talk about things that are very unfamiliar. So one more familiar force is electromagnetism. That is one of the fundamental forces. We have four fundamental forces. Gravity is one of them, one of the ones that we're the most familiar with. Electromagnetism is another one, because we need to turn the lights on, and a lot of our devices use electromagnetism. And one of the things that we learn when we are first introduced to this force is, for example, that if you have two equal charges, that they feel a repulsive force between them. But if you have opposite charges, that they attract each other. And that force is the basis for atomic physics, for example, like having the electrons orbiting around the atomic nucleus, it's all is based on electromagnetic interactions. And so we know a lot about this force, and I'll talk a little bit about some analogies and differences between the force that we're trying to study. When we start zooming in and looking at the nucleus, since we're nuclear, we're nuclear physicists both at FRIB, and then part of what we do is also nuclear physics. We are faced with a puzzle when we start thinking about the various forces. So gravity, one of the things that we know, acts on objects with mass, but there is no such thing as negative mass. And when we talked about like the positive charges versus negative charges, as far as we know, there's no such thing as negative mass. It is also a very weak force. It's much, much weaker than electromagnetism. It basically, at the nuclear scales, it hardly plays any role. Electromagnetism acts on objects with electric charge. And we talked about the fact that these like charges can repel and opposites attract, and that is basically the basis for atomic structure. But once we get into the nucleus, in this kind of little animation that I make for the gold nucleus, which is what we use for Rick, some of the little marbles that are colored there, some of them are the neutrons, the other color is the protons. And we're told already at the high school level that protons are so-called because they have positive charge, and neutrons carry that name because they're electrically neutral. And when we are told all these, and we're told, okay, all of these protons are just, in this very, very tiny nucleus, and the neutrons that have zero charge also in this very tiny nucleus, there should already be a question in our mind as to, wait a second, you told me that positive charges repel each other. So why are they there? Why are they in the nucleus? Neutrons feel no electrical force. Why are they there too? So, and if the protons are repelling each other, why don't the nuclei just explode? So why doesn't this happen? Do this, right? Like this is what we should be doing. All of these matter should just be exploding left and right. If that's all we are told in high school. And so the reason why that doesn't happen, which they don't usually tell us in high school, and I think it's a mistake because you can see that you already can learn about this just with what I just said, is that there is another force, not gravity, not electromagnetism, that keeps the nuclei together. And that force doesn't care whether you're a proton or a neutron, which is why both protons and neutrons are held together in nuclei. And because we're very creative and that force is very strong, we call it the strong force. Because it is indeed the strongest of all the forces of nature. So that's why we call it that, the strong nuclear force. So this is part of what we like to study. Another of the interesting questions that kind of like I came to when I was first got a glimpse that you could do these kinds of studies was this question of what happens when you start going smaller and smaller and smaller, and to really try to understand the basic building blocks of matter? Is there a limit to how small you can make things? And one interesting thing, earlier on we were talking about the origin of words. One word that we learn is atom in high school. We learn about atoms in chemistry and the periodic table. Where does the word atom come from? And it turns out it comes from Greek. And the actual meaning of the word atom, atomos, in Greek means indivisible, which means that we now know we can actually break up the atom because the atom has electrons and a nucleus. We can actually separate the two. So the word atom basically meant that chemists jumped the gun. It's not really indivisible. We can divide it. And so that's part of our journey into going to smaller and smaller scales. So if you look at kind of like an atom and we compare that to our typical human sizes of meters, we're 10 billion times smaller than that. And that's already pretty small. But now we know that we can go even smaller. So that's where the nucleus lives. The nucleus is on the order of 10,000 times smaller than one atom. Well, then we can know that we can go even smaller. That's why we know that these things they gave them names. We discovered the proton, we discovered the neutron. And if we go, 10 times smaller than a nucleus, 100,000 times smaller than an atom, we start getting to the sizes of the proton. And we realize that inside the proton, there are even tinier things. And these are the things that we, again, had to invent names. If you think about all of these names, at some point were new. At some point, someone had to invent the name atom. Someone had to invent the name nucleus. Someone had to invent the name proton and neutron. So in the 60s, the name for the things that are making up the protons and neutrons, one of the proposals was quark, and that's the name that stuck. And so we now know that there are many kinds of quarks that actually help to make the matter around us. It turns out that for making protons and neutrons, you also just need just two kinds. But there are more kinds that I'll talk about a little bit later. But this is one of the questions, like as we start getting into what are the smallest constituents of matter, we got to these quarks. And it is these quarks that carry this funky force. So we now know that there's more kinds of quarks rather than just the ones that you need to make protons and neutrons and stable matter. And all of these feel this fundamental force, the strong interaction. And they are bound in a similar way in which electrons are bound to an atom via the electromagnetic force, and the embodiment of the electromagnetic force is light itself, the photon. The particle that represents the analogous particle to the photon for the case of the strong force is like the strongest possible glue. So again, physicists had to invent a funky name for it, and we call it a gluon. And so the quarks and gluons are the particles that lie at the heart of protons and neutrons. It turns out that because it is a new force, they carry a new kind of charge. And this funky charge behaves in a way that was very non-intuitive. We were used to things like the electrons having maybe one kind of charge and that's anti-charge. We're used to that. So the fact that you have charge and anti-charge adding together to give you something neutral. We had seen that before. But the new thing that was that these quarks and gluons had was that you could also add 3 different kinds of that charge that they carried. And it turns out that you also got something that was neutral. This was something new. And so we had to come up with a name for it. And because it was similar to the primary colors, where you combine 3 primary colors of light to make neutral light, we gave it the name color charge. Not because we think that these things actually carry color the way that we perceive it, but just simply as a way to remind ourselves that we need 3 to also make something neutral, just like the primary colors. And so the name for the force, the name that is given in scientific papers, is quantum chromodynamics, because chromo in Greek means color. And so when I mention color, that's what I mean in this talk. It doesn't mean the usual red, white, and green colors that we see, and I'll use some of those to represent those as visuals. But just to keep in mind that we're really talking about a fundamental charge that these quarks carry that we just call color, because we had to invent something for it, and it behaves very similar to the primary colors. So, so these are the various 6 kinds of quarks that we know exist. Why 6? Nobody knows. But we do know that these are the ones that we have found. And the ones that I particularly study are going to be the charm, the B quark that is called bottom here, but sometimes it's also called the beauty. So I'll talk about those in a bit. And here's the kind of representation of what these colors might do, and how you can combine those 3 to make something neutral. Yes, Paul.
Manuel, do we have any reason to believe that there should be more than?
I know that people looked for additional generations as possible extensions to the standard model. We have not found them, but there was also no reason, like why 3? Why 3 families of quarks? At the very beginning, when one of the reasons why the name strange was given to that quark was because at the very beginning everything worked well. Like, oh, we have these two quarks, the up and the down, that help us explain how protons and neutrons work. And a lot of the particles that we were observing back in the 60s worked perfectly well with those, but all of a sudden all these other particles came up and they didn't fit the pattern. They were very strange. And that's where the name strange came from. And this name kind of stuck. People didn't know what to do with this extra quark, because you had these pattern of 2 quarks making a family that worked very well. The mathematics worked very well. And someone then proposed, what if there's another quark, so that you can complete a family? If you have another quark together with a strange one, you can complete the family and everything will work like a charm. And that's where the name charm came from. So then they realized there's maybe another family, and up and down had already been used. So people picked top and bottom because it's kind of like top, up and down. But, they also, because we already used whimsical names like charm and strange, and people had already used the letters T and the letters B. So people that wanted to be a bit more whimsical started calling those other quarks truth and beauty. And that's why I use the name beauty here, because it's also, I like to tell people that I study charm and beauty for a living. So how do we know about these quarks? I can tell you all, these things that happen about these objects that are, minute and millions of a meter. We learn about this by breaking things up, similar to what we do here at FRIB. We break things up in order to learn things. And the colliders that I've worked on at the Relative Physics Area Collider in New York, and at the Large Hadron Collider in Geneva, Switzerland. So these are two pictures of the two facilities. And let me talk about an analogy with what we know about the structure of the atom, and a difference that is very important for the study of the strong interaction. So let's say that you want to study the structure of an atom. So here's a neutral atom that has some electrons that are negatively charged and a positively charged. And you want to study the structure of this neutral atom. You have to break it up by sending some energy, some particles, so that you can actually now remove the electron away from it. And you can separate the constituents. You really break up the constituents of the atom. And our understanding of electrodynamics would be very, very different if we were not able to do this. If we could not isolate electrically charged objects so that we could manipulate them. Well, now, what happens if you have all these quarks that are dancing around inside our neutral proton, and we don't fundamentally really understand all the mechanisms of why these quarks are all stuck in there. I'll talk about some of the things that lead us to think that the quarks always have to be, held prisoner inside particles like protons or neutrons. If you try to separate them, you need an infinite amount of energy. So if you try to do the same thing, you want to isolate a quark and you shoot an object to try to hit it so that it separates and do the same thing you did with the atom. There's now a very, very, very strong potential energy stored in this funky field. Like I said, it is the strongest of nature. And it also behaves in a very interesting way. If you separate an electron out from a nucleus, the potential energy starts to decrease. Here, basically the opposite happens. The energy grows with separation. And in quantum mechanics and special relativity, when you marry them, if you have energy growing with separation, out of that energy, you can create new particles through E equals mc squared. So you can create quark-antiquark pairs that were not there before. And now you can then continue to have two neutral objects, but you don't have isolated quarks. And so that makes our study and our life a lot harder, but that's also what keeps it interesting. So to understand the strong force and this phenomenon of the color being confined inside particles like protons or other particles that have quarks, what we want to do is to create a system of these deconfined polar quarks and possibly gluons. So how do we learn about these? Here's this one works. I tried to make sure that there was one that actually worked. So the idea is you have these two bags of quarks, the two nuclei that are coming at each other. And when they collide, what we hope is that we are liberating these quarks and gluons so that they can interact via this funky color fields that are being stretched and hopefully create a new state of matter. So here's a little cartoon as to what that might be and why do we smash nuclei in order to study it. And so the name that we gave the state is the Quark-Gluon Plasma. So why did we call it the Quark-Gluon Plasma? But what's a plasma? Again, going back to what the original words, our most familiar plasma is the sun. And it's a different state of matter. Solids, liquids, gases, all of those are states that we're very familiar with. And you keep going from solid to liquid, gas, as you keep cranking up the temperature. If you keep increasing the temperature, you reach the temperature that you can, where you can make a plasma. And essentially temperature here really means that you're just making the molecules or the atoms or whatever this thing is made of jiggle faster and faster and faster and faster. Eventually they start bumping into each other with such force that in the plasma state, the electromagnetic plasma state, the atoms are no longer neutral because you're smashing atoms with such high energy that you rip the electrons apart. And now the electrical energy is manifest. So in the sun, you can basically have a fluid that has all of the electrodynamics equations at the same time being manifest because the electric charge is free. That's what the plasma state is. So in analogy with that, so in here, the atoms are the things that are melting because it's so hot. The electrons and the nuclei are free. That's what our plasma that we're more familiar with, that's what that means. And so what we're trying to do is to now melt the proton and the neutron, to reach the temperatures where we not just melt the atoms, where we melt the nucleus. And now, instead of just having the electrical charge being free, what we would like to have are the quarks and gluons being free. That's why we call it a Quark-Gluon Plasma. So what do we need to do to melt the nucleus? This is a little cartoon where I have all these protons and neutrons with all the little colored quarks inside them, but they're all confined inside, so we don't see them because they're all trapped inside. And one thing we can do is we can heat them up, and you might have like little particles that you know, made of quarks, antiquarks that show up. You can also compress them by doing these types of collisions. And if you compress them enough and heat them up enough, instead of having this overlap of the bags of quarks that are these protons and neutrons, you hope to completely remove their veil so that you can actually see the color charge being manifest, the color being deconfined. That's kind of the cartoon picture. So of course it's a cartoon. Are there something are there things that are more serious than just a cartoon? And that's what this picture is about. This is one of the first pictures of an actual calculation that was done from using supercomputers that on the vertical axis are trying to calculate the energy density of particles made up of quarks and gluons. And on the horizontal axis, you have an increase in temperature. And it turns out that if you have the energy density divided by the fourth power of the temperature, in many systems, when there is a transition from one phase to another, you can see something that looks like a step. And that's exactly what we see here. We see something that looks like a big step at one particular temperature that is in this funny energy units, mega electron volts. And if you ask how much, what are those mega electron volts in units that we're more familiar with, we're talking about hundreds of thousands of times the temperature of the sun, which is why for what we're trying to do, the sun is too cold. So we need to go way, 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 way hotter than the sun. What we're trying to do, these kinds of temperatures are what existed at the very, very beginnings of our universe. 1 microsecond after the Big Bang. That's why when we do these kinds of collisions, we say we're recreating the conditions of the early universe, because that's how hot it needs to get. And so what we're hoping is happening here, what we're seeing is that we're going from a state down here that has just a few options for it to go in. It can go into these quark-antiquark pairs, for example, to a state that has lots of quarks, each one having 3 colors with various spin states and all its antiparticles and all of the gluons. And that is what drives the rise in this graph. And so we hope that maybe at RIC we might be getting to these kinds of temperatures, maybe at the LHC we'll be getting to these kinds of temperatures, but at the time when this first was proposed, this was all kind of speculative. We didn't know whether that's really the case. And that's part of why the measurements that I tried to do, we're trying to get to, like, do we really get to those temperatures that are so unimaginably high. And so that's part of what we're trying to do. But this is an actual calculation with some of the best supercomputers that we had at the time, trying to actually calculate what's happening with the strong interaction with quarks and gluons. And this is one of the best guidances that we have, that such a state actually exists, and we're not just, thinking about a pipe dream. So so that was a calculation. What I like to tell people, that essentially in a nutshell, what we do using analogies is that imagine that you know that ice exists because you've seen cold matter. That's all you know about. The matter of our world compared to this is very cold. So we live in an ice age by comparison. So that's what we know. But your theory friends that have all these giant computers tell us that there's something called water, that there's a new state that you've never seen before because you live in such a cold world. But you don't have a way to heat up ice. That's forbidden to you. You can't just simply let's take the water on the stove. That's what we would like to do, but we can't do that because it's too hot, and we need so much more material to make something like this that we can't do it with our current technology. So that avenue is closed to us. So how else can we heat up things? We put millions of ice cubes in an ice accelerator, and then we set them at 99.995% of the speed of light to collide. And we generate thousands of ice cube on ice cube collisions per second. And then we watch it all from Mars. That's what we're trying to do. That's why it's so hard. Well, this is in a nutshell what we're trying to do when we do these kinds of functions.
There's a question from Forrest Stevers online. Yes, the strongest force in nature, is that what is released in nuclear bombs?
Very good question. And remnants of that are part of what is released in nuclear bombs. The force that I'm talking about here is the force at the level of, we're trying to really get to the fundamental constituents of protons and neutrons that are the quarks and gluons. But a remnant of that is the interaction that holds protons and neutrons together. What they exchange are not directly quarks and gluons, but they exchange, for example, to first order, they can exchange a quark-antiquark pair. And that force is what holds nuclei together. And when we use something like a nuclear reactor or a nuclear bomb, we are accessing that force. And the energy scales are millions of times larger than the energy scales related to chemical interactions that happen at the level of the electrons in atoms, which is why those reactions are so much more powerful. We're talking millions of times more energy per atom compared to chemical reactions. So yes, so we are accessing aspects of the strong force when that happens. Very, very good question. So what I get to do, as I mentioned, I get to play with charm and beauty, the charm and beauty quarks. And I like to study particularly bound states of these objects. And what that means is that we have two of these very heavy quarks trapped by the color force between them, a charm and an anti-charm, a beauty and an anti-beauty. And they have these funky names. The charm anti-charm, people thought that it was the closest analogous state that we had seen before was a particle antiparticle state. When you take an electron and you take its antiparticle, a positron, you can actually make an electrically confined bound state called positronium. So people call this charmonium because this is, by analogy, a state of matter antimatter, but now being held together by the strong interaction. So people call that the charm anti-charm state charmonium, and for beauty anti-beauty, beautyonium or bottomonium, depending on whether you use bottom or beauty. And they have all these funky names, letters that are given for each of the particles. Like, for example, one particle, because it was discovered by two groups at the same time, one group called it the J, another group called it the Psi. So it's one particle that has two names, J, Psi, and then it has excited states, like the Psi prime is an excited state. And a similar system in the B quark sector is the upsilon. That's the Greek letter upsilon, and there's excited states for it as well. And there's similar, some of the properties and the quantum numbers are very similar to what is given in spectroscopic notation in atomic physics. And so there's S refers to the angular momentum of that particular state. And so we actually use the similarity to this excited states of electrons in atoms to describe some of these. And it's really nice to work with these for us because we basically are using quantum mechanics, which is a lot simpler to use than full-fledged quantum field theory that sometimes is needed for doing calculations in other particles. And speaking of quantum mechanics, here's some pictures coming from the quantum mechanics view of what these particles do and how they behave in what we think might be something like the potential that binds these quarks together. So what is shown here in this plot is a potential energy diagram. That's this one here, where this black curve is meant to represent what we think might be a good approximation to the potential between these two particles. And the thing that you notice here is that this potential rises, which is one of the things that is very, very different compared to the electromagnetic potential, where the potential basically at some point just flattens out. This one, that's the part where if you try to keep separating the two quarks, there's more and more and more energy. That's part of why that linearly rising part is very important. And the key is that people are able to take these kinds of potentials and work out what the quantum properties of these states are. Here's one such example of what we think the quantum wave functions, which are ways of telling us where the quarks might be in space, are for the various beauty states. And one of the things that I'd like to draw your attention to is that, for example, this red part is the ground state of this beauty-antibeauty. And you have various excited states that in quantum mechanics are represented by things that have more and more waviness in these funky wave functions. But the other thing that you notice is that those numbers that are listed in the plot are giving you the average distance between the quarks. And by studying the various states, we can vary how close the two quarks are together. And so the red ground state, the quarks are very, very, very tightly bound together. So the units here are femtometers, 10 to the minus 15. This is like 1/5 of the size of a proton, roughly. And so you go from 1/5 to about 3/4 the size of a proton. A proton is roughly 1 in these units. And so we, by studying these states, are able to kind of vary the energy of the state and also how close the quarks are to each other. And these are some things that we can do thanks to the fact that these are very heavy quarks, and so they're not moving very fast, which is why we can use non-relativistic quantum mechanics. So that's one of the reasons why I also think that these are very useful for us to study. So because of that, we know a lot of properties about these quarks. So here's that simulation that's there is coming from a group that was also doing these supercomputer simulations, kind of showing that if you try to separate them apart, that funky cloud that kind of shows up in between them is a representation of that amount of energy that's contained in the gluons that keep those quarks glued together. And by doing these kinds of calculations, we are able to find a lot of the properties of these states. We know what their masses are. Roughly, this is in these units, giga electron volts. A proton is roughly 1 in this unit. So this is basically 3 times the mass of the proton. The one that I like to study is almost 10 times as massive as a proton. And we know, as I mentioned, how far apart the two quarks are. We know how much energy we need to give them in order to break them apart. And so the more energy we need to give them, for example, at this one, we need to, the one that I was mentioning here, you need to give it as much energy as one whole proton in order to break it apart. Whereas for some of the particles, you need to give them a lot less. This one, where's my arrow? Where's my arrow? Oh, here it is. This one right here, you basically like almost breathe on it, and you can basically dissociate it because it needs so little energy for it to dissociate. Now the caveat, of course, the full production of this is complicated. There's people that spend their entire careers trying to study the properties of these particles. I will not get into that. That's a whole other topic. But the thing that I wanted to mention, and I think I already touched on it before, is that the potential in electrodynamics is such that it flattens out eventually. But for the potential for the quantum chromodynamics for the color force has, in addition, this linearly rising part that is what keeps the quarks confined. And what we think is happening when we collide things in a heavy ion collision and produce a Quark-Gluon plasma, this is kind of like where what I study can tell us something about the plasma, is that maybe, so if you make this quark, so in this particle, so in this particular example, here's the charm-anti-charm pair that is made, but in this case, you are making it in a proton-proton collision, so it's not surrounded by all these additional quarks. And so it's bound and it does what it does its thing. You can measure them in these collisions. But what we like to do is to say, okay, compare that to what happens when you actually put them inside this soup of other quarks. It turns out, and this was an idea that was first brought about in the mid-80s, that when you put these quarks around the other heavy quarks, that the potential that they feel, this attraction that keeps them bound, is going to be changed. We call that effect screening, because it's like someone draws a veil, a screen, and you can no longer see the person that is in front of you, so you can't dance with them. And so the idea is that the Quark-Gluon plasma introduces this interesting length scale that depends on the temperature, that as you keep increasing the temperature, the amount of screening, the amount of like how far you can see the other object that you're dancing with gets smaller and smaller. And at higher temperatures, you can dissolve more of the states. Yes, Pablo.
Temperature seems to be super important in everything that you're calculating and doing. And I can think of temperature when I have like a macroscopic cube of ice and it melts. But if I have number of quarks, when I'm imagining this that I can count with my fingers or the fingers of all my friends, I don't know how to think of temperature anymore.
That's a very good question. One of the reasons why we do heavy ions is because that hopefully allows us to get a system with as many particles as possible so that we can really treat it as a thermal bath. And interesting enough, and this is a surprise to me as well, because when the concept of temperature that we're used to works really well when we have a drop of water or something like that has Avogadro's number of particles in it. But here, we don't have anywhere close to Avogadro's number. We have thousands of particles maybe. It's still a good number, but 1,000 is way, way, way smaller than Avogadro's number. The fact that it works so well is still kind of a question as to like, are we really doing the right thing when we treat things thermally? So far, what people do is we do have models that treat the system as a fluid in thermodynamic equilibrium. And it actually works very, very well to describe the data, which is somewhat surprising. It actually works surprisingly well, given how few particles we have. Part of it, I think, is the fact that the system is so strongly coupled that it really does behave kind of like a liquid, even with those few particles. So, and this was a surprising finding. It was not obvious at all. So that's definitely a very, very good question. But yeah, in all of this, I'm assuming that yes, we can treat and talk about temperature, and one of the things that I'd like to do is try to find out how hot it actually is.
Yeah, exactly.
Yes.
How much of a differentiation of the distance, or was it comparable or corresponding with Planck's constant or Planck's length at all?
Very good question. So here we're still very far away from the Planck length. So I mentioned that we are talking about, if I go back the slide.
That's more what I meant. If
we're talking about like this radii are on the order of femtometers, 10 to the minus 15. The Planck length is on the order of 10 to the minus 34.
Before, I was just wondering if it corresponded to it by any chance, or if it followed any.
An interesting thing to think about is that, so we're meters, right? These things are femtometers, 10 to the minus 15. So the Planck scale is to quarks smaller than quarks are to us. That's how far removed the Planck scale is from all of this. And that's why like doing things at the Planck scale is so hard, because this is already the limit of our technology. Femtometers, 10 to the minus 18 maybe.
Right.
So 10 to the minus 34, we have no means currently of accessing such small scales directly. And and that is still an area of research for other people that are trying to unify gravity with quantum physics. But this is still way bigger than the Planck scale, comparatively speaking. Yeah.
Excuse me.
Yes.
I'm trying to understand your surprise. I mean, there are two limits. There's several limits where you can have statistical physics. One is on the one system that's very large, and there's also ensembles of small systems. So what sets a scale here that says that an ensemble of small systems will give you the wrong physics?
I think that it wasn't obvious that
Well, that's true. It wasn't obvious, but still it comes back to the question, what sets the scale? I mean, you could imagine that you have a system that has to be a certain size to manifest a certain property, but I don't see what that size is.
And I think that that's still an active area of inquiry within our field. We're still trying to, so part of what I'll mention in the talk is kind of one interpretation of the data that I have, but I certainly am aware that we still don't yet know where that size limit is. People are trying to push the boundaries, and the best that we have right now is like, we know that
Somehow relates to how complicated is a fundamental system. I mean, if the system only involved, while the degrees are manifested with a small particle system, then it's hard to say that a very large scale is needed.
yes, and we're still trying to see, for example, if we don't have yet an answer to the question, can we make this state, this Quark-Gluon plasma, for example, really in a very small proton-proton collision, or how if it is, how big is it? We still don't have the answer to those questions because we don't know yet how small can the system get. So that is still an active area of research. Yeah. So what I like to do, again, to share you a cartoon, is the following. We are producing these beauty-antibeauty states. So here's my cartoon of a beauty-antibeauty state. So I turn the beauty upside down because I don't know how to draw an anti-bottom quark otherwise in a screen. And there is that bound state. And it's going to traverse through this colored medium. The colored medium dissolves the state, melts it. It doesn't mean that the bottom quarks are no longer there. It means they don't see each other anymore. They're not longer dancing together. They can then pair up with another quark at the end to make up a different kind of particle. It's called a B meson, but it's no longer the bottom anti-bottom quark bound state. That's kind of the cartoon picture of what our experiments are trying to do. And so what do we learn when we do this? What we're trying to tell, one of the things that we're trying to tell is, for example, how can we gain information as to the temperature of the plasma? Because we think that the hotter it is, that the shorter that the screening length we have to get. And because we have all these states that we can use to measure in our experiments, some states, like the 3s state of the upsilon, is much further separated, less bound. And so it should melt at a smaller temperature. And so by measuring as many of these states as we can try to get information as to how hot it actually gets by doing the comparisons. Do you have a question? But that's the idea. You have some states that are very, very tightly bound together, very short distances between the quarks. Those states are going to be much harder to melt. So you need hotter and hotter temperatures. And what we try to do is to see, do we see evidence of that when we do our measurements? And so here's kind of another view from different calculations. So this is from Georg Wolfschen in Germany, where he compares in this calculation what the wave functions of the different states would look like at different temperatures. And so in the top plot now, you see the difference between what you expect to have at 0 temperature versus what happens at very, very high temperature, where some of these states are now much, much broader than what you would normally associate them to be. And so the expectation is that maybe the 1s state doesn't change very much, or maybe it doesn't even melt at all. Maybe the 2s state does get modified, maybe it's likely to melt, and maybe the 3s state, because it's so far apart between the two, maybe it's fully melted. A caveat here is that these particles feed into each other, like the 3s state can decay into a 1s state and things like that. That complicates the picture, but once we discussed that with our theory colleagues, they've now included those things into their models. One particular complication that happens for the case of charmonium, which is why I look at bothonium or at beauty-onium, is that there's enough charm quarks in the collisions at LHC that you might actually remake charm anti-charm states because of all there's enough charm around. But beauty is so heavy and so rare that you at most make one of them in one collision, and that simplifies things. It makes your life hard because there's rare, but it makes your life easy in that, okay, if you know that there was only one and that's it. And so that simplifies things. And so, so does this static thermometer, here's the caveat, because I know that we have some experts here in the room. That's a very nice little cartoon picture, but life is way more difficult than this. The temperature profile is not uniform. The quark-gluon formation time is not necessarily as well defined. And there might be other things that can lead to quark-gluon melting. I mentioned already the charmonium regeneration contribution and the feed down. So the people that do this, they do things in a way more complicated and complex way than I've described. There's a whole dynamical approach to evolving the plasma. And so that's the work that my theory colleagues are doing. My work is to try to measure these states and to look for evidence that, that beauty-bound states melt. So thinking about my work, how can we actually see them? How do we see these beauty states? So I mentioned that this upsilon particle has a mass about 10 times the size of the proton, or 10 times as massive as a proton. We can see it via its decay. So the way that it's produced, I have some diagrams that illustrate gluons that you can grab from the incoming nuclei that end up making this little blob here, that is the quark-gluon state. And that quark-gluon state, that blob is what I mean by this blob over here, that you have this bottom anti-bottom that then annihilates because they're particle-antiparticle. And since they're particle-antiparticle and they can annihilate, you can then get another particle-antiparticle pair that you can actually see in your experiment. In our case, for CMS, muon and an anti-muon, for example. And so that's a cartoon. Here's the actual CMS detector. And just to give you an idea of the scale, so here's our standard human compared to the compact muon solenoid, which always gives me a kick of the fact that they called it compact, this thing. It's 5 stories high, but they call it compact. So here's another human, so that you can get the scale here again. And these very, the largest detectors out here, outside of the large solenoid, the S stands for solenoid, the compact muon solenoid, are the muon chambers. And the muons are so important for CMS that they put it in our middle name. So we always like to say muons is our middle name because we can do muons very, very, very well. So thinking about muons, here's a blow-up of one of the pictures that I had before. This is one way in which we can find beauty. Here's an event display of one of the first heavy ion collisions that we collected. This is from 2010. This is an upsilon candidate. We say a candidate because we're never sure whether this was really an upsilon or not. But it quacks like a duck, it looks like a duck. It's most likely an upsilon candidate and an upsilon meson. And the way that we see it is because we see very clearly this muon track out here in the muon chamber. So here's a picture from the, as I mentioned, from one of the first runs. Here's a picture from LHC run 2. One of the things that you can notice is that these collisions indeed produce thousands of particles. They are, they're the equivalent of many thousands of proton-proton collisions happening at once, and all of them are dumping particles into our detector. That's why you see all these yellow tracks and the Lego kind of figure there of those blue and green blocks. is electromagnetic and hadronic energy flowing out of the collision. And there's lots of it. But thankfully, very few things actually decay into muons. So when we see two muons, they really stick out like a sore thumb. And it makes it very easy to say, hey, that event is interesting. There are muons in it. Let's grab it. Let's analyze it. And so we are looking for these telltale signs of beauty when you see these two muon tracks. And that makes our life very simple because we have these beautiful muon detectors in CMS. And so here's those were static pictures. Hopefully this one works. I can pause it a little bit so you can actually see some more of it. That's the particle train. They collide and produce all these particles, depositing energy in the detector. And in this particular event, there was one single muon track that you again see sticking out. Like a sore thumb all the way out here. So that's a one muon track among thousands and thousands of other particles that they had in this event. So let me now introduce some of the actual measurements that we do. And before I show you the data, let me tell you what exactly are we trying to do? We're trying to measure something that we call the nuclear modification factor. What's the key idea behind this thing? The key idea is that you measure a particle in heavy ion collisions. That's ultimately our goal. So that's what we put in the numerator. So the idea is that this is what happens when there's a QGP. That's the goal. And the idea is you measure that same particle in proton-proton collisions. That's a reference measurement, but as we just were discussing, ideally they say there's no QGP, but as I mentioned, we're still debating as to whether or not there's a QGP in there. But first order, let's say there's no QGP there. But we now need to know, okay, you have a heavy ion collision. As I mentioned, there's the equivalent of many thousands of collisions, of PP collisions happening in one single heavy ion collision. So we need to take that into account. And that's this factor that you see, the number of collisions and call, to try to kind of construct a ratio so that you have how much did you measure of this particle, the upsilon in PP, you multiply that by how many collisions you expect there should have been in that corresponding lead-lead collision, and then you compare that to what you actually measure. So you obtain this ratio, and the idea, the way to read this ratio is that if there's nothing interesting happening, no medium effect, that ratio should be exactly 1. If there's less particles, the particles production is suppressed, you see a ratio that is below 1. And if you see an enhancement, that means that you see a ratio above 1. And there's a caveat here that, there's mentioned that there are other nuclear effects that are not to do with the hot Quark-Gluon plasma. And that's still an open question. How do you actually extrapolate? And that's one of the things that I'll also show you, that we've done measurements also in proton-nucleon collisions to try to get to those effects. But here's the actual first kind of like one of the, first, this is like this is like already the run 2 results, because those are some of our best ones so far. But what you see here are 2 plots that basically are showing the same thing. In the vertical axis, how many events we measure at a given mass that we obtain by reconstructing the trajectories of those 2 muons and seeing how much energy the hypothetical parent particle would have. And as I mentioned, the particles that we're looking for are roughly 10 times as massive as the proton in these funky units. So that's why you see these very dramatic peaks that represent those particles that we're looking for. And this is the measurement in proton-proton collisions. So this is our reference measurement. Once we obtain the reference measurement, knowing the nuclear geometry, we can say, how many should we expect? And that's that dashed line in this other plot. The dashed line is how many do we expect to have if there was no difference? And you'll see now where the data are. And the data are way lower than the dashed line. That means we have suppression. So that dashed line is that scaling that we would obtain if the ratio that I mentioned was 1. And so we are observing clear suppression of these states compared to the production that we would have expected if nothing interesting was happening.
And the suppression is not uniform. Like I need to multiply the blue curve by 3 or 2 point something on the first peak, but probably by like 10 on the second peak.
And this goes already back to one of the things that I wanted to mention, right? We mentioned that the states have
that makes sense.
ISIS. And so we absolutely hoped to see that the suppression for each state event would be different. That is exactly what we hoped to see. And that is exactly what we saw. We also, as I mentioned, did the measurement in proton-led collisions. So again, this is basically that same plot that I showed before. This is the PP collision reference. And we again can superimpose what we would expect for proton-led. And we also do see suppression, but you also notice that it is much less pronounced than the suppression that we saw in lead-lead collisions. And so a possible interpretation is that there is some breakup of the final state beauty states, but that the large effect that we see in lead-lead does need a hot, color-screened quark-gluon plasma. That is one of the possible interpretations. But as I mentioned, we're still, as experimentalists, we do the measurements and we're seeing whether we can rule out various scenarios. We're very excited about looking at the excited states. In the first plot that I showed you, the suppression, particularly for the 3s state, was so severe that we didn't really see statistically significant signal. Typically, you want a 5 standard deviation signal. And this was done a little bit later. You see that this was only published last year, where we improved the analysis so that we could actually see, and this little inset here is a kind of a zoom in into this little region here where you see that it's so hard to distinguish from the data compared to this blue dashed line, which is the combinatorial background. It's a very, very small signal that we're looking for, but we worked really hard and we were able to extract a signal for this very loosely bound excited 3s epsilon state. And so this was the first ever measurement of the 3s in nucleus-nucleus collisions. And we only published this last year. So this is really cool. And let me give you one additional plot, but before I show it to you, I want to talk about the other knob that we can turn as experimentalists. We call this knob the centrality of the collision, which is essentially how much overlap there is. And a peripheral collision is basically a collision where the two nuclei barely touch each other. And that's kind of like what's happening in the cartoon. That small overlap, that little small oval region is where you actually are producing particles. The rest of the particles basically just go through each other and they keep going. And so in this case, so all of this stuff doesn't collide with anything. It's only this little region that is colliding. So there is less matter that participates in the collision. The volume is much smaller and likely it is much less hot. And contrast that to a collision where the two are almost head on. We call that a central collision. And basically that's kind of when you hit the bullseye. You can imagine that that's rare, but we can actually tell. I'll show you in a second how we can tell. And here, almost all of these nucleons are participating in the collision. You see there's this very, very large overlap. And so we have a large volume and the hottest collision. So we can think about and try to do the measurement and compare what happens in these types of collisions compared to what happens in these types of collisions. But remember, these are femtometer distance. It is really interesting. How can we control the distance? And the answer is we can't. We don't control it. We just, after the fact, can tell what type of collision it was. So how can we tell? How do you tell a head-on collision? So this impact parameter is in the order of a few femtometers. So those collisions where the impact parameter is 0, that are very central, that are very head-on, produce lots of particles. So what we do is we can look in our tracking detectors and we see what are the collisions that produce the most particles. And we can compare that to the case where you have a peripheral collision, and we can clearly tell when there's less participants, that's the way that it looks like in those events. There's a lot fewer particles, and that's how we can tell. We cannot tell exactly what the impact parameter was, but we can tell statistically, this is a peripheral collision versus a central collision, and we can get classes of events that are more central or more peripheral. When we do that, and we look at this ratio of the various particles, this is what we see. As you look at the collisions where the overlap is very small, the collisions where they just barely touch each other, is grazing, the ratios are much larger. As you start going to more and more and more central collisions, there's more and more and more suppression. The ratio gets further and further and further away from 1 to the low end. And so this is how we can tell how hot it's actually getting. When we give this data to some of our theory colleagues, and this is what Pablo, you were pointing out, that there is a pattern of suppression where the excited states are more suppressed. Our theory colleagues are the ones that can put all of this information into the models of how the system is evolving, how hot it's supposed to be getting. They can vary their temperature, they can vary some of the parameters, and then give us some of the information about that. So here's just one example, just to give you an idea. This is from the Texas A&M group, Ralph Rapp and collaborators. So here's a comparison that they had to the data for the upsilons in CMS, and their curves are their theory calculations. And there's a lot of information about the model here. I don't think we necessarily need to go very much into, but so for example, like when do the states melt is part of the input, and they can vary their initial temperature. And what they expect is that indeed you get temperatures on the order of 500 to 600, 700. If you go back to that first picture that I show you of, this is well into the region where the calculations tell us there should be a Quark-Gluon plasma. And so this is part of the reason why we think we are getting into that zone where we are forming a Quark-Gluon plasma by looking at these data. So here's kind of a summary of all of the data that I show you. These are all the various ratios of the 1s, 2s, and 3s states. The blue points are kind of the summary of what happens in lead-lead collisions, and the red points are what happens in p-lead collisions, showing kind of like the difference in the level of suppression when you have a very small system compared to having a very, very large system. And basically, it has taken us like 10 to 15 years to collect all of the data that you see here, which is really, it's really cool to see all of it come together, giving us the story. And during this, got a chance to actually do the film that we're going to screen on Sunday. So hopefully some of you got tickets for that. And I also like to showcase some of the actual students in my group who got a chance to be in the film, and some of them were the ones who actually do the work. Some of their thesis projects were what I just showed you. So with that, I hope I convince you that we can study the strongest force of nature in some of these largest collider facilities in the world, that these beautiful quark-gluon states are a very useful way of trying to probe the color force between quarks. And what we saw is this amazing suppression of this beauty-antibeauty pairs. And it's consistent with the formation of a very hot Quark-Gluon plasma that melts the beauty states. And our understanding is coming from a description of a very large body of data. As mentioned, this is over a decade of study. And it involves a dynamical picture of this strong color force that is actively melting the beauty particles. We're very excited that the LHC Run 3 is currently underway, and we have a lot more beauty to explore. Thank you very much.
For a beautiful talk, very interesting stuff. There's a question online from Forrest Stivers asking, are quarks actually liberated in this nuclear collision?
That's a very good question. In some of the models they are, but the honest answer is that we don't know if the quarks are actually liberated. The very first models and the very first ideas as to what was going to happen at these temperatures is that indeed the quarks would be liberated. But little by little, the community has come to realize that life wasn't as simple as we thought, and to really be sure that that's what's happening. We don't yet have the evidence to say the quarks are being liberated. It could also be that there's other states that are quark-bound states, but not just the ones that we're used to, that also carry color. What does seem to be clear is that the color force is manifest. It might not be that the quarks themselves are totally acting as free particles. It could be that they're still very strongly coupled, but whatever new system that each of the quarks makes is now, having color being deconfined. That does seem to be the case. But whether the quarks are liberated, I think we cannot yet say that yet. Yeah.
Let's take a couple more questions. Yeah.
Would you use a secondary system, like if you had two of these simultaneously happening near each other, near enough that those muon pathways could be kind of connected to one another because they could maybe, I don't know, maybe the quarks would be interacting with the other system and trying to repair with the other system, not just their own system. And you could maybe use that to see if you're extracting it. Really complicated, but
I think, people are trying to do something similar to that with the charm system. Because as I mentioned, with the charm system, there's enough charm. Charm is lighter than beauty. It's still heavier than a proton. And the charm anti-charm state is 3 times as massive as the proton, but 3 times is less than 10. And so at the LHC energies, there is enough charm produced in one single collision that one of the things that people have to take into account is the possibility that you might have formed uncorrelated pairs of these heavy charm quarks, but that they end up finding themselves at the end of the collision when it refreezes, and suddenly you have these states. That's something that people actually do see, and they need to take that into account to understand the data in the charm sector.
Very good. Well, let's take one last question. Yeah. Sure.
But I remember from introductory particle physics that the top quark is so heavy, doesn't live long enough to form a bound toponium state.
Yes.
If that were the case, you could form a toponium. Would that be a better probe than the bottomonium?
Very good question. It's indeed like it's so short-lived that it basically just doesn't make a bound state. If it were to make a bound state, it would be interesting to try to study it. What we do with the fact that it does decay, we actually use it in a different way, or at least we're hoping to, because it's so rare that even right now, when we've published the first observations of top in heavy ions, it's been done with like 100 events. So it's very rare because it's so massive. But what we hope to do, and this can give you an idea of how challenging it can be, is that because it decays so quickly, and it essentially decays 99% or more of the time into a beauty quark and a W boson, which is the carrier of the other force that I didn't talk about, which is the weak force, the weak nuclear force, which is because it's different than the strong interaction. The W bosons don't feel the Quark-Gluon plasma. And so when they decay, and way in which the W bosons can decay is, say, into a muon and a muon neutrino. We can actually measure all of those particles in our collision. We can measure, I mentioned the muon. The mu neutrino can actually be measured. Our detectors are hermetic enough that we can actually detect the missing energy of the neutrino and tag that as this was energy that was missing and obtain a neutrino that way. And that way reconstruct a W. And the B quark produces a jet of particles that can be reconstructed, and we can actually tag it as containing a B quark. But that requires basically using the entire suite of tools at our disposal. It means missing energy, it means muons, it means jets, and it means tagging a displaced vertex within the jet. It's one of the most complicated analysis. And then you're only getting like 100 events. So, but the goal is, if you have that, you know that you have a W and you have a B quark. And the B quark, as it traverses the plasma, can also lose energy. And there's a whole suite of measurements trying to understand the properties of the plasma from the point of view of how quarks pass through the plasma, losing energy, radiating gluons, and doing a whole bunch of fun things that I didn't get a chance to talk about. That's what we're hoping to use the top quark.
Awesome. Thank you.
Thank you very much. Thank you, Manuel, for a beautiful talk and Have a great weekend. For those of you online, thank you for joining us, and we'll see you next time.